we found out the rate law using the initial rate. There are other ways to determine the rate law. We're going to talk about a new method called using the integrated rate law. It's a graphical method. Unfortunately, it's difficult to work examples of the graphical method in this format. It's much easier if we were in class. All right, so I'm going to skip through that. But the integrated rate laws, while the integrated rate laws can be used to determine the order of a reaction, there's another application for the integrated rate laws. So it's easiest to explain for the first order reaction. We can take a first order reaction, and it is a reaction that's taking place, and the rate becomes equal to this change in concentration as a function of time. We saw it. We saw it in our observations of the reaction. So the amount of A as a function of time. Reaction starts fast, goes slow, 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 slow. Right. There's a formula for this line. This line, it follows a regular progression. Right. And the regularity of that allows us, we can take the slope of that line, that's our rate, at any given moment. All right. Conversely, if we know the rate and the rate constant at a given time, we can figure out how much is going to be left at some future time. All right? Because the rate is equal to K times the concentration, and so we can then predict into the future. All right? So this allows us, we can basically take integrate this arrangement, and we're not going to do any integration. We're just going to integrate across this and take, knowing the rate constant, we can figure out an equation that relates this not to concentration and rate, but to concentration and time. We can use the relationship here, this concentration and time. Right? And this is the form for the first order rate law. Right? There are two variations of this that are exactly the same, just written in different forms. I prefer this version because it's easier to work with, in my opinion. And so we can use these to relate the concentration at some time t to the initial concentration. So these subscripts, some time t and some initial concentration. This is the integrated rate law, allowing us to relate time to concentration. And so these problems talk about, well, how much material is left over after 30 minutes, right? Now we can average this. We could take an estimate. We know what the rate is right now. We can take an estimate, but we can do better. We can use the mathematical relationships given to us by the chemistry. All right. All we need to know is that it's first order, all right, or second order, or third order. There is a version of this relationship for every order. Knowing the order, you can use this integrated rate law for a first order reaction. Natural log of A at time t is equal to negative K, rate constant, times the t in the right units, times plus the natural log of the starting concentration. And so this is the integrated rate law. Very easy. This is actually a linear relationship, so if we actually take the log and plot it as a function of the natural log of the concentration as a function of time, we can get a linear relationship and extract out this information, but we're not going to do that. All right, I'll show you that later just as an example, but we're not going to have time to do that. All right. So let's take a look at an example of this. Decomposition of hydrogen peroxide is first order with respect to H2O2, and they tell us that. Right? So we already know that's a first order reaction. They say the rate constant is X, 1.8 times 10 to the minus fifth. If you start at 0.75 molar, how much remains after 3 hours? All right. So this is a very standard problem. We're told what it is at some time, so we've given our rate constant K is equal to 1.8 times 10 to the negative fifth. And the units for that are inverse seconds, first order rate law. If the concentration is 0.50, so that's H2O2 at time 0, we know that it's 0.750 molar. And so we know it's first order. We know it's, we can then use this relationship. We can say, okay, well, what is the ln at time t? So this is after 3 hours. That will equal negative kt plus ln a naught. And so whatever the concentration was at time 0. So we plug in that 0.75. And the only thing we have to care about then is plugging in our time. Now this is the only real thing you have to pay attention to, that this time has to be in the same units as our k. Here it's seconds. So that is 3 hours is 10,000 seconds. And so we can then plug in those values. And so we get ln H2O2 that we're looking for is equal to negative 1.8 times 10 to the minus fifth times 1.08 times 10 to the minus fourth, times 10 to the fourth seconds, plus ln 0.75. We'll run through this calculation. This will give us the number. And so doing our math, we get ln H2O is equal to this value here, 0.481. And then we take the we raise this to the power, raise e to the power of negative 4.8 to undo this. E, in this case it's negative number, so we have to take into account the e to the x. And so I get the concentration of H2O2 after 3 hours is equal to 0.618 molar. It's gone down a little. So it makes sense too. The amount of hydrogen peroxide has gone down, and it's gone down a little for this particular rate. Leading mistakes is how to undo this natural logarithm. All right, at e to the reaction, so e to the negative x, or making sure the signs are taken care of appropriately. Okay. So let's try the same one, but with a slightly different arrangement. So instead they say, how long does it take for H2O concentration to drop to 0.01 molar? Okay, so the same reaction, I'm just going to use A at this time. A at time t is equal to ln A at time 0 minus kt. That's how I like to write it. This number, they tell us that this is 0.1 molar. They say that we want that target to be 0.1 molar. Right? Most of the reactant is gone. This is going to be 0.75 molar. And now we're going to figure out what this value is. And so we can plug those values in. And I'm going to do the math on those. So we convert our values. We take the logarithm, natural logarithm for the A at the future time. We take the logarithm for the A at the current, at the starting time. We get these numerical values and we plug them into the equation, and you're left with one variable, the time. And so we can then rearrange and solve for the time. So in this case, we had 2.30, subtract out minus 0.278. So this gives us 2.01 negative is equal to negative 1.8 times 10 to the negative fifth t in seconds. Again, this is a seconds, inverse seconds, so second time would have to be in seconds. Right? And this is good. The negative signs on both sides cancel out because you can't have a negative time. Right? And so, especially not in chemistry, it's always a positive time in chemistry. And so we can then solve for the time. And so I get 7.1 times 10 to the 5th seconds, or 31 hours. So, all right, so after 2 days or so, most of the hydrogen peroxide will be gone. All right. So the integrated rate laws are excellent for, given this set of conditions, figure out how much is left. All right. So that's for first order reactions. So the first order reactions, you can rearrange them, and it turns out that this is a linear equation. We're not going to do this, so you can shut off your brains at this point. You can pick them up again in about 5 minutes when we talk about the next order. But you can see that this is a linear relationship. Mx y is equal to mx plus b, where b is a constant. And so you can tell from the slope, if you plot this the right way, natural log of a as a function of t, this line should be straight. And so you could then determine that graphically. And so you can use that information. And so that's actually how we figure out things are first order or not. Okay, you can turn your brains back on again. What's nice about the first order rate law, and particularly this only applies to the first order rate law, is that it doesn't matter where you start, what the concentration is. As the reaction progresses, the time it takes for it to drop so that half of the starting material is used up is the same as it takes to drop for the next time length to drop halfway. So say it again, every certain unit of time, half the material will dissolve, and that unit of time will be consistent for this material. These are called half-lives. So the half-life is the time it takes half the reaction to disappear. And for the first order reaction, if you start with this, half of it will disappear. After the same unit of time, another half will disappear, half of that half amount. So there will be a quarter left, and then an eighth, and then a 16th, okay? So that actually follows a very regular progression, making it easy for us to use a simplified version of this called the half-life equation. Right? The T1 half, the time it takes for the half the reactant to disappear, is equal to 0.693 K. This only applies to first order reactions. Right? So you can figure this value out knowing the half-life. You basically watch the reaction until half of it disappears, and then you take that time, and from that you can easily obtain the rate constant. Right? So in other words, if you take 0.693 and divide it by that time, you get the rate constant. And that's a very quick and easy thing to do. One set of reactions that applies to this are nuclear reactions. Okay, so one of the ways you've heard the term half-life before is in the terms of nuclear chemistry. The half-life can be measured for radioactive isotopes. They undergo a decomposition that follows first-order kinetics. And so if, depending on how radioactive the material is, you can chart the decomposition of the isotope using half-life measurements. Measure the radiation that's coming off of it. So here's a very simple reaction. The decomposition of ethane is first order. Reaction constant, they give you K, calculate the half-life in minutes. Now, you could use this long equation here, but we're going to use the short one. 0.693 over K is equal to T1 half. Right? Whatever the units of K in, this will be T1 half. And so we'll look at the units of K. The units of K will be in seconds. And so they wanted to inverse seconds. So this, whatever time we get out will be in seconds. So we literally just plug our rate constant in. I'm not going to show that. Clear 0.693 divided by 5.36 exponent -4. And I get a half-life of 1,300 seconds, 21 minutes. So after 21 minutes, half the material will be gone at this particular temperature. Right? Again, very powerful for a first order reaction. Very little calculations. And then the second half-life will be another 21 minutes. At that time, we know that it'll go from whatever the original concentration is to half what it was, and then half again, so about a quarter of the amount. Now, second order reactions are pretty much the same. They also have an equation that applies to them. For a second order reaction, it's a slightly different form. 1 over A at time t will equal 1 over A at time 0 plus KT. All right? And so functionally, you just have to memorize a different equation. I'm not going to do any examples for that, but they behave the exact same way. You know that it's second order. They say it is second order and has a rate, and the rate constant is given. You can figure these things out. Here are 2 examples to work through. So that's using the integrated rate law to measure amounts of material. Right? So there are 3 here. So here are the 3 major integrated rate laws. These are the important things that you care about. The rate law, the integrated rate law. We don't really care about the half-life equation except for the first order rate law one. All right? A 0th order reaction may seem weird, but some compounds, some do not play a serious role in the chemistry. And those are really challenging because you'll double the concentration, the rate will stay the same, and you won't understand why it's happening, but that happens. Okay?